The next will be Ricarda Beckmann from the University of Cambridge, simulating the origins of the first supermassive black holes. Ricarda, please go ahead. And I'll give you a warning in 10 minutes.
Okay. So yes, my name is Ricarda. I'm currently a postdoc at the University of Cambridge, but most of the work I want to present today is work I did in collaboration with Julian Divrier and Adrian Sliss at the University of Oxford while I was there. Sorry. So this is another simulator talk, so it sort of fits nicely into the context of the last talk we heard. And what I want to discuss today is a fairly simple question, really at the heart of high redshift quasars, I guess, and that is, how did the first black holes become so massive? So this is a plot a little old now. You know, we heard earlier that the sample of high redshift quasars and their black holes has grown massively over the last few years, but you can see that if you look at the distribution of black hole masses on the y-axis relative to the redshift and the x-axis, some of the first objects we found are already as massive as the most massive objects we see across the history of the universe. Now, you know, this part of the plot has now been filled in more, but the basic point still stands. They're all in this region. And that leads to the interesting question, which is, how did the first supermassive black holes get so massive in just about 600 megayears, which is about the time you have between the first sort of plausible black hole seed formation scenarios to the time when we start observing the first supermassive black holes. So how do you make a supermassive black hole? This is Black Holes 101, but sort of very simply is you have to start with a seed black hole. That's a whole field of research, is how the first seed black holes formed at very high redshift. And it's not a topic I want to go into today, because I really want to think about how these seed black holes then grow and possibly become supermassive throughout their evolution. And there's two potential growth channels. You can either merge black holes together to make a bigger black hole, or the black holes can accrete some of the gas from their host galaxies and grow through that channel. And my work focuses on this gas accretion channel, so I will be disregarding this black hole merger channel now, so there will be no mergers, and we will instead think about how you can study the accretion of gas and how much gas accretion might contribute at very high redshift to the growth of supermassive black holes. So as I said, this is roughly the sort of parameter space we have to cover. So this is the same plot as before, now just extended to lower black hole masses and higher redshifts, because in the bottom right corner here, we've got marked sort of roughly the region of where we think the seed black holes might form, both in their redshift and mass range. So they go from these POP3 scenarios, which would form the smallest seeds, possibly at the highest redshift, all the way to sort of direct collapse black holes, which already upon seed formation are several orders of magnitude larger. But even the most massive of these seed channels leave a large gap between where we think the seeds could form and where we observe the first supermassive black holes. And from there, after seed formation, they grow, and how efficient this growth can be in this particular environment is still an open question. People have been working on this for many years, but it's still very much not well understood how much black holes actually can grow via gas accretion. Here we've got sort of a few cartoonish lines where you can roughly see some proposed evolutions, with the Eddington ratio sort of being a measure of how efficient black hole growth is. Generally, Eddington ratios can fall very low, less than 1%, 0.01, even lower. So all of these proposed lines here are very efficient gas accretion, and you can see that really for these black hole seeds to make it to the observed masses, they need to be extremely efficient. The Eddington ratios need to be very, very high. But the problem with studying the gas accretion, and especially the problem with, you know, trying to get that much mass into the black hole, is that the gas that has to be accreted by the black hole has to flow over a very large range of length scales before it actually reaches the black hole. Black holes are massive, but they're incredibly compact, which means that the actual scales in which they accrete and interact are very small. And the gas really has to flow, you know, from the cosmic environment into the host galaxies, through the host galaxies, past these sort of interstellar scales where all the sort of star formation and stellar feedback goes on. It has to get sufficiently close to the black hole to reach the region where the black hole's gravitational potential dominates the local environment. So it can be attracted into that, fall into the bottom of the potential, and then finally reach the last stable orbit and be accreted. And you can see that even for a very massive black hole, this is a very large range of scales. And the smaller the black hole, the smaller these sort of scales at the bottom end here get. Now, this is a huge numerical challenge for simulations, including all these scales in one go. And which is why typically we're going to have to make a choice on how many of these we include in a single simulation and try to study at the same time. A typical, what we call a zoom simulation, which focuses on individual galaxies at high resolution, tends to cover this range of scale. So it's a choice where we tend to follow gas flows all the way from sort of intragalactic scales through the galaxy and inside the galaxy. But the problem is that you notice here that actually in this particular context, in many cases, the actual scales where the black hole dominates, so where we could really make a judgment on whether the gas is gravitationally bound to the black hole or not, tend to be unresolved in these kinds of simulations. So I spent over a few years a lot of time and effort trying to push the range of scales we can resolve in a single simulations near the black holes far enough that we can actually start resolving some of the gas flows right around the black hole and start understanding how much of the gas in the galaxy would actually be able to reach the black hole in this particular context. So this is an example. At the top, I've got a simulation minus the sort of algorithm I've added, where you can see on galactic scales, we have beautiful detail. This is a simulation with about parsecs worth of resolution, which is very good for this kind of length scales that we need to follow the simulations to understand black hole growth over 600 megayears or so. But if you look sufficiently close to the black hole, we very quickly start losing information, and very close on the sort of parsecs or parsec scales, there's very little information left since we're only looking at a single pixel. Now, with my zoom algorithm, this is what we get. On the large scales, the simulations are virtually identical. We retain a lot of the information, but we were able to add a targeted extra refinement around the black hole that's allowed us to retain and recover a lot of this information right near the black hole as we run throughout the simulation. Which has made it possible to try to study the gas flows from the intragalactic scales all the way to the sort of black hole dominated scales in a single simulation. Obviously at increased cost, so it comes at a price of other trade-offs, but it's still, I think, a huge step in the right direction. And I want to show you today why it's so important that we study gas flows, not just on the galactic scales, but actually on scales much closer to the black hole itself as well. So what I wanted to understand was, how does resolving the subparsec black hole environment influence accretion, particularly in the context of trying to grow the first supermassive black holes, which have to sustain these incredibly high accretion rates over time. So before I get all the way to the early universe, I want to show you a little test case first. So this is the simulations I just showed you the images of. Dark blue being the high resolution case, the beautiful bottom row, dark red being the top row of images, which the lower resolution. And in all three panels, I compared how the black hole grows in these environments over fairly short time scales. So we're looking at only about 5 megayears here. All black holes start out identical, and then you can see they all accrete very efficiently. So over time, the mass of the black holes changes very quickly. But the first thing you will notice is that, first of all, the lower resolution case actually was more efficient at accreting. That makes sense because we were removing gas on larger scales since we don't have any information on small scales. So the black hole actually grows much more efficiently over time. And the higher the resolution, so the higher the number of the simulation here, the lower the total black hole accretion drops. So there's something there to understand that on smaller scales, accretion becomes harder. The other thing to notice that if you compare the black hole accretion rate over time, which is in this middle panel, especially the red line, which is in comparison to, say, the dark blue line here, you will notice that the red line is very choppy. So the accretion rate very quickly jumps up and down. And that's because on the scales we're resolving, every time a gas clump enters the center of the galaxy where the black hole is, it's immediately accreted by the black hole, the accretion rate jumps up, and then as the gas sort of is gone, the accretion rate jumps back down until the next clump enters sort of the center of the galaxy. But you will notice that in the higher resolved simulation, this is not true. We tend to get these more extended, longer spikes followed by long, low periods where the accretion rates drop much lower. And the reason for that is that if we look at the central region around the black hole, what we start building up very quickly here is we start building up a nuclear disk. So this is not the accretion disk. We're still at scales far above where you'd think classically study an accretion disk, but this is clearly a disk-like structure in the center of the galaxy, in the potential of the black hole, that is feeding this black hole over time and also acting as a buffer to the accretion. And what happens is, over time, we get gas clumps falling into the center. So this is the plot where we got radii on the y-axis. So these markers here are two gas clumps that fall from large radii, so over 10 parsecs, to near where the black hole is. There's a second one coming in a little later. This is a time series. And as these gas clumps fall in, the black hole accretion rate here shown in the black dashed line spikes up, which is what you'd expect to happen is. But the interesting part is the mechanism of why that happens is. Because what we've also shown here is this orange line, which is the outer radius of this nuclear disk. And as these gas clumps come in, it's not just that the clumps get accreted, it's that actually as they disturb this nuclear disk, the nuclear disk contracts due to the transfer of angular momentum in this process and delivers a extended accretion feeding event to the black hole, which then grows for a good period of time until the disk resettles and the accretion rate of the black hole drops off again. So actually during this accretion event, more mass is delivered to the black hole than is in the individual clumps, and it's much more extended than it would have been in the simple case when we were just looking at the actual, when each clump just got individually accreted as it got there. So what we took away from this is that these parsec-sized gas features in the potential of the black hole can change the black hole accretion duty cycles in a way that's very hard to predict from super parsec-sized gas features. So basically, there's an amount of information there that's very hard to recover from larger scales, which for me is a very strong argument that we do in fact need to go to these lengths and look at these incredibly detailed, expensive simulations to study how these black holes grow in this particular context. So what about the first black holes? Well, if we do put one of these high-resolution black holes into a cosmological setting and try to understand, how do we get from this bottom right of this plot here, from one of the seed black holes, can we make it all the way to the observed regime? So this is a simulation, as I said, in a full cosmological context, using the super refinement scheme. Won't bore you with the details, but we basically picked a halo at around redshift 20 and seeded a black hole in it and then let the evolution of it run. Does it grow? This is the interesting part. It does not. So, or rather it does very efficiently early on, but it certainly does not reach the observed mass regime. So this is the total mass of the black hole. We started at about a few hundred solar masses, so sort of in the POP 3-star remnant regime, and we let the simulation run for about 200 mega years, so about a third of the total evolution time to where we see the observations. But then we gave up because, as you can see, the evolution very quickly started stalling. And the reason this is very interesting is because this is still a very simple simulation. So this is a simulation without feedback. There's no stellar feedback. There's no feedback from the AGN. So this is a very gas-rich galaxy assembling at high redshift that should have plenty of gas supply. We see very high sustained star formation rates. This is clearly not a lack of gas in the galaxy. And yet, despite this very simple model where we have removed some of what we know is crucial physics in this environment that tends to suppress black hole accretion, we still don't get the runaway sustained growth that we expected in this particular environment if you look at it at these incredibly high resolutions. So if you go back to this plot, how much did we do on this plot? We started down here, redshift about 19, a few hundred solar masses. There was a very early accretion boost, so the black hole actually grew super Eddington very efficiently as we expected it to. There was not much to hinder its growth, but then growth very quickly stalled. And despite the lack of feedback, we had actually found very low Eddington ratios over time, and we got to about this far, and then decided it wasn't worth the computational time to try to continue since there was very little evolution. And in fact, if you look at the black hole accretion rate, you can exactly see that there was a very, very high initial growth rate. As expected, the black hole was born in a high gas galaxy. But then very quickly, over time, we get these incredibly low accretion rates. This is the Eddington accretion rate here in gray. So you can see that the ratio between the black line and the gray line drops very low. And black hole growth effectively stops after the first sort of 50 mega years of evolution. Star formation, on the other hand, continues not completely at the same level, but certainly at much higher rates than the black hole growth. So there's clearly an ample gas supply. And when we try to understand why the black hole doesn't grow, we found that there's a very strong correlation, obviously, between the gas supply local to the black hole and the accretion rate, which makes sense. Black hole accretion rate is calculated based on the local gas properties. So if you got locally a lot of gas, then the black hole can grow. But we actually found that the correlation only really holds for very small scales. So in our case, we found a strong correlation between gas mass contained within a parsec of the black hole. But if you go as far as just 10 parsecs away, which on intergalactic scales is not a lot. We found basically no correlation between the gas supply and the accretion rate of the black hole. So that showed us that there is a lot of gas on scales very near the black hole, but actually most of it is not bound to the black hole or not on an orbit where it's able to be accreted by the black hole, so therefore cannot act as an effective gas supply for the growth of these black holes. And a look at the images revealed where, to a certain extent, the issue was. So at the top here, we got a series of pictures that show us 4 different snapshots from redshift 6.84 to 16.18. We can see the galaxy with these sort of beautiful spiral arm structures, and the black hole location is marked with this black cross. And you can see the black hole is certainly in the galaxy. It is certainly near the center of the galaxy, but it's not precisely located at the center of the galaxy. So what ends up happening is that the gas supply of the black hole becomes very, very localized. There are times when the black hole depletes its local sort of orbit almost completely. There are other times when it passes through gas-rich features and able to sort of pick up some extra gas, which drives these accretion spikes that we saw earlier. And then over time, the gas supply becomes depleted again, and the black hole is again not able to tap into this existing gas reservoir in the galaxy. So again, we found that subparsec-sized gas features can change the black hole accretion duty cycles in a way that cannot easily be predicted from the superparsec-sized gas features. So part of this is that again, we were trying to understand whether we can use the information on these larger scales, since this is what's more easily, more cheaply, more commonly available in simulations, to try to study the black hole growth in these simulations over time. And again, we found that in fact there's very little correlation between the information on the larger and the smaller scales, or at least it's not as simply as linking the amount of gas on, say, 10 parsec scales near the black hole, and that does not provide you a reliable accretion rate onto the actual black hole, even in this incredibly simplified scenario where we've neglected the sort of feedback effects. So in conclusion, what we took away from this is that resolving subparsec-sized gas features fundamentally changes the accretion and therefore possible later feedback duty cycles of massive black holes. Increasing the resolution decreases the gas accretion rate onto the black hole in general, so more information actually makes it harder to accrete, which makes the challenge of growing the first supermassive black holes even harder than we'd maybe appreciated before. Even in the absence of feedback, black holes are not able to grow indiscriminately, because if studied at sufficiently high resolution, the dynamics of the black hole, so where exactly it is located in the galaxy, becomes a much more important feature, again, than we maybe appreciated before, because the gas supply of the black hole is so localized, and its effect on the larger galaxy can be so limited in this particular context. And I'll leave you with that, and
right. Thanks so much. Great talk. So you can unmute and applause. And quite a few questions. And we had quite a few questions here. Let me just, because of our level time, let me just one.
Shall you have to unmute yourself when people are done clapping every time? Sorry.
All right. I have to unmute again. Sorry, because we're over time. Let me just ask one. So, Nick, how set up initial conditions, because observed black holes are very rare, 5 to sigma fluctuations. Actually, Tom has a related question of these are extremely rare objects. Every answer may be correct, but only sort of usually they don't grow, but in rare cases they might.
Yes, so that is one of the big limitations of this work. So a lot of this was done at a time before some of the results that we now have about the host galaxies of the first supermassive black hole. So I'm thinking of the results from the blue tide simulations. So what we did at the time, we simply went with an overmassive region. So we picked the progenitor of the most massive galaxy at redshift 6 that had the correct number density, following the logic that the most massive black holes are probably found in the most massive halo. But it's absolutely correct that, you know, the big problem here is that we might be studying in excruciating detail the wrong area, right? And that is a big limitation. It's something I've been thinking about for a while on how to do that better, because part of the problem with this is that, you know, because these simulations are expensive, we can obviously not afford to do them terribly often. So trying to solve the problem of knowing which halo to study before we have to run the simulation is one of the big problems. and definitely one of the big challenges of this work.
Right. Thank you. And there are a lot of more interesting questions in the Slack, so I just
I'll have a
suggest
look at
you
the Slack
continue
and
those
do my
discussions.
best to answer.
Great.